All right, thank you, Jacob. So today I'm talking about BackXPress, and that is a novel interaction technique that uses back-of-device finger pressure to augment touchscreen input on smartphones. So you probably all use a smartphone on a daily basis, and you use them in different ways, and also you hold them in different ways. So for example, the most prominent case is probably the one-handed portrait-oriented mode, where you use the thumb to interact with the touchscreen. Or if you need more precision, you might use both hands and use the index finger of the dominant hand to interact with the smartphone. Or if we want to take pictures, or if we do two-thumb typing, we hold the device in landscape orientation. So what you see is that we're only actually using a few fingers to interact with the touchscreen. So what about the other fingers? So if you take a closer look, we can see that they are actually used to hold the device in place. So they are resting at the back, or they are resting at the side, and that's independent of the orientation or how many hands we're actually using. So it's a little bit sad that we don't use these fingers for interaction, but of course research has also looked into this. And this is called back-of-device interaction. And one of the most prominent examples, I would say, is Lucid Touch or NanoTouch from Borchers and others. So what they did is they used very small screens and attached a digitizer to the back of the device. In this way, they can overcome the occlusion problem, so they don't interact at the front, but they interact from behind, basically. The problem, however, with these approaches is that I have to move my finger in the location from behind. And at that point, I might lose the stable grip that I'm actually using. So in this case, I have to use two hands, for example. One hand is holding the device, and the index finger from the other hand is interacting at the back. Now think about if I'm using two hands, it becomes even more complicated. So if I'm moving all the fingers at the back, the device might just drop. So we thought about using or looking at another property of touch instead of the location. And this property that we looked at is pressure. And pressure has become more prominent now in smartphones. For example, here, the iPhone 6s. So the thing is, I can exert pressure while the finger is resting at the same position, but I'm still very expressive. So while I'm pressing, the menu here or the mail pops up, I can peek to it as long as I'm maintaining that pressure. So I'm in a certain quasi-mode. Now when I release the pressure, I automatically flip back, so we have a natural inverse that's going on here. So there's no need for pressing for a back button, for example. So pressure input on mobile devices is not new, so we also have examples in research. And one example is a work by McLachlan and others. So what they did is they attached a pressure sensor to the bezel of a tablet. And this way, the hand or the thumb of the hand that is usually just used to hold the tablet can take part in the interaction. So when I'm pressing, I'm entering quasi-modes, and I can then use the index finger from the other hand to interact in that quasi-mode. Another example is from Wilson and others. So they applied pressure sensors at the sides of a smartphone, so I can hold it in place, and I can still use these fingers that are holding the device in place to interact. So we thought about combining pressure input and back-of-device input. So we basically have the benefit that the device can still be in place, and I'm very expressive, and I have all the benefits of back-of-device interaction, so overcoming occlusion problems, but also using these fingers for the interaction. So let me give you an example that shows how BackXPress works. So on the right-hand side, you can see that the user is holding a smartphone in landscape orientation, the two thumbs are resting above the touchscreen, and the fingers are resting at the back. The user is currently playing a point-and-click adventure, and you probably all know that how these games work. So you have a list, an inventory of objects, you pick an object, then you are in that mode of this object, and then you have to tap or to click somewhere to apply that object to the scene. So with BackXPress, we can make use of the quasi-modes. So when I'm pressing my finger, a menu pops up showing the inventory. The harder I press, the further the cursor moves to select an object. So and while I'm maintaining that pressure, I can then interact with the thumb at the frontal touchscreen to apply that object at its current location. And as soon as I release the pressure, the menu automatically fades away. Another example is typing with two hands. So here we have a keyboard. And as you can see, we are in the standard mode where we have small letters. But now let's say I want to write a word in capital letters. So all I need to do is to press with the index finger at the back. The keyboard layout changes to capital letters, and I can use my thumbs for typing. And I can also use it, for example, for entering digits. And as you can see, I can use both thumbs at the same time, basically, for entering text. Or even a shorter example is when I want to insert a single character, like an emoji. So again, here, I could use another finger, press to browse through the emojis, tap it, release the fingers at the back, and I'm back at my standard keyboard layout. So this is the idea and then some examples of BackXPress, but the questions that we had, of course, are, okay, how does this work for users? What are its limitations? And we basically had 3 different research questions, and each question was addressed in a different study. I will only show you the main results of the first 2 studies. You can read the details in the paper, and I will talk a little bit further about the 3rd study. So first of all, we need to know which fingers users can actually use to comfortably exert pressure at the back of the device. And it also includes questioning, okay, what device size and what orientation is actually feasible here. So we found out that a smaller device size, for example, 4.7-inch device, hold in landscape orientation works best because that gives you a very good way of exerting pressure. And it allows users to use index, ring finger, and middle finger to exert that pressure from both hands. Next, we looked at where actually the users are then pressing. Because if you think about having a continuous pressure-sensitive surface at the back of the device, at some point you want to know from which finger that touch actually came from. So, as I said, you can use one finger, for example, to pop up the emojis, and use another finger to go into the caps mode, for example. So, and then the third and the most important question is, of course, how accurately can users actually apply back-of-device pressure and then tap at the same time at the front? So this was covered in our 3rd study, and we had basically 2 tasks. The first task is one tap, and that's basically similar to inserting an emoji. So you exert pressure for a very short time, tap, and then you release. And the second one is called end tap, and that is basically maintaining pressure over a longer time, for example, when you want to type in capital letters. So this is the setup of our study. We sandwiched 2 iPhones back to back. The back was pressure sensitive. And then we asked the users first to navigate pressure using a certain finger. And that was indicated by the white bar that you can see here, the so-called finger indicator. So the top right basically meant use the index finger from the right hand. And then we had pressure menus. You can see that in the left and the right in different colors. So here we have 7 discrete pressure levels. And then we had a cursor, and the user would exert pressure, and that cursor would update at that point. Then we also see the target, and you can see that the ring of the target, the color matches basically the current pressure level, and the color of the crosshair, that matches the target pressure, so the pressure that the user was to reach for. So when you can see, as soon as the 2 colors match, that was the signal for the user to tap with the thumb. So in the one-tap condition, we had several independent variables, but I'm only covering a few here. We looked at different menu sizes, so a baseline condition involving no pressure at all. We had 3, 5, and 7 menu items. Then we looked at all the different fingers from both hands, and we had 8 touch targets in total. It's important to mention that we ignored the resting pressure, and that is one of the beauties that pressure has in comparison to touch input at the back of the device. So when my fingers are at the back, they are touching the device. But at that point, I really don't want to do any input. So with pressure, I have to actually press to engage a little further to voluntarily say, okay, I now want to enter a quasi-mode. We also locked the pressure up on tapping contact. So when the user was navigating the pressure at the back of the device, and then when the thumb was touching the screen, they could release basically their finger. It wouldn't have any effect. That's basically to release the burden from the user of maintaining that pressure as long as the thumb is in contact with the screen. So we looked at different dependent variables, and one of these is time, so the task completion time. So the baseline condition involving no pressure is basically just tapping at the front with the thumbs, and yeah, that's pretty fast. When we use pressure at the back of the device, the time increases by about 2 seconds on top, but please note that this also includes that we are navigating within a menu, which we don't have in the baseline condition. We also looked at the finger, and we could see that the ring finger was significantly slower compared to index and middle finger, although the difference is just 100 milliseconds. Then we also looked at the success, and that basically means, was the user actually at the pressure level that we asked him for when the thumb was touching the screen? And we can see that the success rate decreases with increasing number of menu sizes. So the best that we could get here was 87%. Looking at the finger, we could see that the middle finger performed significantly better compared to index and ring finger, and we believe that this is the case because the middle fingers are positioned at the center, so you don't really push the device or tilt the device compared to the index and ring finger. So in the end tap condition, we asked the users to maintain pressure for 20 seconds, and therefore we also introduced a pseudo-independent variable called time block, where we split everything within 5 seconds of blocks. And we had similar touch targets. Again, we used a pressure lock, but it would only last for a single tap, since in reality we would not know how long a user would be typing, for example, in capital letters. So we did not look at the time because that was fixed to 20 seconds, but we looked again at the success, and we can see that the results are very similar compared to one tap, slightly better. The finger basically had the same results, and looking at the time block, we can see that users performed significantly worse within the first 5 seconds compared to the other time blocks. So that indicates that they need some time to get familiar with the task. We also looked at the tap count, so how many taps could users actually make within the 20 seconds while trying to maintain the pressure. So in the baseline condition, we get the best that is possible, basically, no pressure involved, about 23 taps. And then as soon as pressure is involved, this drops a lot. But the thing is, normally you would expect, okay, users need some time to navigate to the pressure level, and then they can just tap as in the baseline condition. But that's not the case. So sometimes the pressure is a little bit dropping, and then they need to correct until they can tap, so that costs some time. We also split this up into the time block, and we could see that, of course, in the first time block, the taps were significantly lower because they needed to navigate the menu. And comparing the time blocks, we could see that there was no significant difference between the 5 to 10 seconds and the 10 to 15 seconds block. So interestingly, what we also saw is that pressure exertion has no influence on the accuracy of where the thumb touches at the frontal screen. So the error of that distance was about 2.5 millimeters, but it was independent of whether pressure was involved or not, which is good. But still we thought, can we actually improve this? And what we did is we looked at the pressure curves from the users. And what you can see here is the green bar, or the green area, is basically the target pressure that we asked the user to be in when they had to tap with the thumb. And the time when the thumb touches the screen is given here as 0 seconds. But you can see that the pressure is above the green bar, which is bad. So the success would be counted as negative. And that is because when the user tries to move the thumb towards the touchscreen, something is changing. So the pressure either increases or drops a little bit. So what did we do? We basically looked backwards in time over the pressure levels, because in BackXPress, we have a very clear pattern of interaction that's going on. Navigate the pressure first and then tap. So at some point, the user will have chosen the right pressure, and then he will tap. So we averaged over the last 500 milliseconds, and at that point, we get a very good estimate that is within the green zone here. And this way, we could improve our results significantly. Here's an example for one tap. The results are similar for the end tap condition. So in the 3 menu size condition, we could see that we could only push it a little bit further. But if you look at the menu size 5 and 7, it's about an improvement of 10%, which is quite a bit. So what are the design guidelines of BackXPress when we want to use this? So we recommend using a landscape-oriented device, and that gives you back-of-device pressure input for index, middle, and ring finger, so 6 pressure-sensitive regions when you're using both hands. Apply pressure lock upon frontal tapping, and ideally use 3 pressure levels above the normal resting pressure, or if absolutely necessary, you can also use 5 levels, but be sure to use a 500 milliseconds pressure history lookup. And also, if you don't need all the fingers, go for the middle fingers first, because users can control pressure with them much more precisely. So for future work, we already started building a more lightweight case. I actually have that with me, and you can come to me after the session if you want to try it out, or you can find me also at booth D36 in the demos and interactivity. So that basically tackles the problem of having 2 heavy iPhones back to back, basically. Also, regarding the interaction, we would like to look at multi-finger same pressure exertion to combine different quasi-modes. and also looking at gesturing with the thumb instead of just tapping. And you could also think about bringing this to other device classes, like tablets, for example. So this concludes my talk. Thank you very much for your attention, and I'm happy to take your questions.
Don't be shy. Questions?
Hi. Sarah Morrison-Smith, University of Florida. So you said that you're planning... Oh, to the mic? Okay. Sorry. Sarah Morrison-Smith, University of Florida. And you mentioned that you're going to be looking at gestures with the back-to-device pressure. And when I was reading your paper, you said that you were planning on using the pressure lock so that like in order to handle the issue of like shifting when you're, anyway. So that seems like that would work really well for single stroke gestures, but I'm wondering if you've thought about like multi-stroke gestures, because like if you have the pressure lock releasing as soon as the thumb like comes up, then you'd have to like do it again.
Right, so the problem is once you release the finger again, you might have changed the pressure, and at that point you need to read the pressure sensor again, right? Because the pressure lock is gone. And at that point, some big inconsistency can appear. And that is the thing that we want to look at. So how big is this inconsistency? Can we maybe model that? So is that like a way that, okay, with strokes, it's like always changing by, I don't know, like 6% or something in the pressure range. And then we can basically try to model for that. But the thing is always with pressure, of course, we can't do it in reverse, so we can't push your finger out, basically. So that is kind of a tricky thing that we'll probably, we'll find out and have to tackle when we look closer at it.
All right, thanks.
Time for another question or even two? All right, well, I have a question. Jacob Wilbrock, University of Washington. Thanks for your talk. I'm curious about if you looked at all or had a sense from your study of the kind of refractory period from the muscles exerting pressure and how much recovery time the muscles would need in the fingers to exert pressure again. So if you were in a situation where you wanted to rapidly exert different pulses of pressure on the back of the device, how quickly can that be done? Is there fatigue involved? Do the muscles kind of need a bit of a recovery period? What are the implications for your timing? Things like that. Because it seems like the more rapid action was on the front of the device, right? But what about trying to take somewhat rapid action on the back of the device?
So the thing is, rapidly exerting pressure is kind of tricky. So because you always start at zero, and controlling pressure is quite difficult for humans. Unless you go for an infinite target width. So basically, when you press as hard as you can, at some point the sensor won't sense pressure input anymore. So you can reach that very, very well. We didn't include that in our study, so if we would have included that, it would have simplified the task, and I guess that the success rate would have pushed up a little bit. But I think that's tricky, and I also think that there is some fatigue. So what we could see in the end-tap condition is that in the last time block, the success rate already dropped a little bit. So it needed some time to get going, and then it was stable, and then it dropped. So I think if you do it further and longer, there will definitely be some fatigue.